Hi, welcome back. Tomorrow we're going to take a look at something called an iterated integral. Now an iterated integral is just what we call a double integral, and the use of it is very similar to what we did last year in single variable calculus. It's used to find area. So let's say we have a function that's in terms of x and y, and we have this area. We want to find the area underneath this rectangle. Now from calculus last year, we were given integrals, so like in calculus, if I was getting an integral from f of x dx from a to b, that's telling our domain on the x-axis goes from a to b. The same is true for an iterated integral, except for now we have two integrals, and this is what it looks like. Now it looks very complex, but it's very simple to follow. Inside you have your partial derivative, and then you have this dy dx. Well, this dy dx is the area of a rectangle. We're going to talk about that much more later on. But right now, we just want to take a look at, well, how do we get the domains? Well, we think of it as an order of operations. You're going to start with the inside function first. And what this is telling us is that we are going to first just integrate with respect to y. And this is telling me that the change in my y values, or my range for this, is just going to go from 1 to x. So if I come over here, I might start at 1, and we're looking to the area up to x. Working away to the outside now we have, so once we deal with the inside, now we deal with the outside. Now the outside is dealing with my change in x, and the change in x goes from 1 to 2. So we can say our change in x goes from 1 to 2. And I can go here from 1 all the way to 2. And what we're looking for is just this area. So if I kind of draw a rectangle kind of going like through here, what we're looking for is the area underneath this curve, but above 1. So we're looking for the area in this rectangle that is like below that curve. So we'd be looking for this little area right here. This would be the area we are trying to find. Now, note, this distance right here is our delta x. This height here is our delta y. And if you notice, we get a rectangle. Like if I were to multiply those together, delta x and delta y, that becomes an area, length times width, which is where we get this dy dx. Because remember from last year, we say as delta x goes to 0, this becomes dx. As delta y goes to 0, this becomes dy. So as these get smaller, as these distances get smaller and smaller, we're looking at very tiny little rectangles that we're just going to add up. And we're just going to keep on adding up all the very tiny, infinitely tiny rectangles until it fills in this little area. And what adds up all of those tiny little rectangles, lengths and widths, is our double integral, is our integral. So this is very similar again to what we did last year. We're going to spend a lot more time on this over the next few days, so hopefully it'll make a lot more sense for you. But right now, let's practice how we can solve what we call a iterated or double integral. Now, here's a big note. The outside limits must be defined. In other words, the outside limits have to be numbers. These have to be numbers, okay? The inside limits can be a variable. We'll talk a lot about that. Sometimes it's not a variable, sometimes it's not. We will talk about this. But must be in with respect to the other variable of integration. We'll talk more about this later on. But so let's take a look at a couple of problems. So here we have number 7. And we are looking to solve this double integral. Oh, it looks complex, but it's not so bad. Starting with the inside function, the inside integral, that's where we're going to start with. We are going to hold x as constant, just like we talked about in video number 1. So we're going to hold that x as a constant. And when I integrate this with just respect to x, x is the constant. So we're going to integrate with respect to y, So this becomes 1/2 x squared y squared plus 1/3 xy cubed. And I'm going to evaluate that from 1 to x. Applying the fundamental theorem, we will get f of x minus f of 1. Solving it, this is where the fun begins. Plugging the x, and we're going to plug these in for y. So remember, that's why it says right here, must be with respect to the other variable of integration. So if I'm in terms of y, I should be plugging in x's into my y variable. So this becomes 1/2 x to the 4th plus 1/3 x to the 4th. Remember, if I plug x here, x cubed times x is x to the 4th. Plug in the 1, plug it in for the y, right? That becomes 1/2 x squared. And over here, plug in for the y, and that becomes plus 1/3 x. Now, I'm going to leave this alone. I don't like to change anything. So if I so now, I'm going to work the outside. So now I'm going to integrate my whole answer here. This is 1/2 x to the 4th plus 1/3 x to the 4th minus 1/2 x squared minus 1/3 x dx. And this is going to be evaluated from 2 to 4. Oh, these are fun to do. And if we do that, ready, when integrate, this becomes 1/10 x to the 5th plus 1/15 x to the 5th minus 1/6 x cubed minus 1/6 x squared, and we evaluate that from 2 to 4. All right, and I'm going to go and get my answer right here. Ready? This becomes 4 to the 5th over 10. I would not expect you to know that. Just leave that 4 to the 5th over 10 plus 4 to the 5th over 15 minus 4 cubed. We should know that one. 64 over 6 minus 16 over 6. 16 over 6 minus, then we got to plug in the 2. 2 to the 5th, we should know that's just 32 over 10 plus 32 over 15 minus 8 over 6 minus 4 over 6. And leave it alone. Leave it alone, okay? If you want to get bored, I think that becomes 151 or something like that, if you want to simplify that. All right. Fun times, huh? Now, quick question. Does the order in which we integrate matter? And the answer is yes. If we switch these around, it does make a difference. We need to think area. Okay? We need to think area. If last year, we would say, remember from last year, if I'm looking for the area under a curve, or to a curve, to the y-axis right here, if I want to measure this area to the y-axis, and this goes from, let's say we're going to go from 1 to 4, and of course this would be 1 and 2, of course this is like our square root of x right here. If I want to find the area to the y-axis, right, if I go horizontal, if we did a horizontal rectangle, which we probably should, we are in terms of y. If we chose a vertical rectangle from last year, we had to be in terms of x. So if you switch the order of integration, you have to switch your variables. So we would need to use inverses to find the function and the domain. And I should say range as well. We would have to use those inverses from last year. There's a wonderful video on that last year. Alright, hope you had enjoyed this. We are going to talk a little bit more about these later on. You can go and try number 8 if you get bored. But let me show you real quickly how we can actually even do this on a calculator. So the CAS is a really cool little calculator right here. Mine's taking a little bit longer to load up. I probably haven't used it before in a while. So I